Alright, chapter 6.1 is exploring the graphs of polynomial functions. I broke this up into two sections. The first section is just basically looking at all of the different graphs, and then the second section is just a kind of a characteristic sheet just for you to use kind of as a reference when you are graphing. So end behavior is this description of the shape of the graph from left to right on the coordinate plane. So you start on the left, start on the left side of the graph, and you say in quadrant 2 that it is positive, goes down into quadrant 4 where our graph is negative. Okay, and that's not quite as specific as you're going to be, but you're always starting from left to right, just like when you're reading across. Or you might say the graph starts in quadrant 3 with negative values for your y's and x's and y's, and then you describe how it ends. So it might end positive in quadrant 1, or it could end positive or negative in quadrant 4. So your turning point then is any point where the graph of a function changes from increasing to decreasing, or from decreasing to increasing. For example, this curve has two turning points since the y values change from decreasing to increasing to decreasing. So one of those turning points would be right here, and the other one would be right there. The second graph here does not have turning points because the y values are always decreasing. So remember, we're always starting from left to right. So from the left, it's negative. Your values are going down in quadrant 2, and they continue to go down in quadrant 4. They could have even less of a curve and be going down in quadrant 3 as well. A cubic function is a polynomial function of the third degree whose greatest exponent is 3. For example, function of x is equal to 5x cubed plus x squared minus 4x plus 1. Your domain is the set of all possible values for the independent variable in a relation. So that's usually your input value or your x. So that's independent, meaning you can pick whatever value you want and put it in there. It doesn't matter what your other things are. You can decide which value you want to use. Your range then is the set of all the possible values for the dependent variable, as the independent variable takes on all possible values of the domain. So basically your dependent value is your output value or your y, because your y will depend on what value it's going to have, or your y will be dependent on whatever your x value is. So if you take a look at this equation here, function of x is the same thing as substituting in a y. So what my y equals will depend on what value I choose for my x. So just looking at some graphs. So we're going to graph the functions on the same set of axes using different colors and labels. So for number 1, we're graphing y is equal to 7. So y is equal to 7. You go up 1, 2, 3, 4, 5, 6, 7. 10, that's a nice straight line through there. So this is y is equal to 7. My next graph was y is equal to negative 2. I thought I might be able to do shape recognition with this, but okay, so y is equal to negative 2. 1, 2 is down here. So that's my graph of y is equal to negative 2. 2a, y is equal to 2x plus 3, and b, y is equal to 3x minus 7. So these are linear. So if you remember, this is from our slope-intercept form, where m is equal to your slope and b is equal to your y-intercept. So my ay is equal to 2x plus 3. This is my y-intercept, so I plot that first So 1, 2, 3. My slope is equal to 2 over 1. So from my y-intercept, I rise 2, 1, 2, run 1. And I can go the other way. I can fall or go down 1, 2, and over 1. So if I connect my dots, and you can use a ruler and make it a little bit nicer, this is what this graph would look like. Y is equal to 3x minus 7, so I start with my y-intercept of negative 7. 1, 2, 3, 4, 5, 6, 7. My slope is 3, so that's the same as 3 over 1, so I rise 1, 2, 3, run 1. Or I could go the other direction and go down 1, 2, 3, and to the left 1. So if I connect my dots, this is the graph of y is equal to 3x minus 7. Okay, the next graph, y is equal to negative 2x minus 5, and y is equal to negative x plus 7. So the first one, negative 2x minus 5, my y-intercept is negative 5. 1, 2, 3, 4, 5. My slope is negative 2 over 1. So negative 2 means I have to go down 1, 1, 2, and over 1. Or I could have went up, done a positive rise, 1, 2, but then that means I have a negative run. So I connect my dots. Oh, that's really not that straight. Let's try that one again. There, that's a little bit better. So this is y is equal to negative 2x minus 5. Second equation, y is equal to negative x plus 6. So y-intercept of 6 and negative, so this is like negative 1 over 1. So I go down 1 over 1, or I could go rise 1, then I have to run a negative. So if I compare my graph 2 with my graph 3, I can see my graph 2 is going from negative to positive, if I read it from left to right, and my graph for question number 3 are going from positive to negative. So if it is a positive slope, your line rises to the right. So like example 2. If it's a negative slope, your line will fall. So like example 3. Y is equal to x squared plus 0. So x squared plus, y is equal to x squared is the same as saying x squared plus 0. So that means that I'm starting at the origin, and every time I go over 1, I'm going to go up 1. If I went 2, then my input is a 2, so if I go over 2, then I'm going up 4, because I have to square it, and so on. So then it'd be 3 and 9, and 4 and 16, and so on. Y is equal to negative x squared minus 4. So that means that this is my, if you remember from graphing, your P and your Q. So we have y is equal to a times x minus p squared plus q. So this means that my a value is a negative 1. I don't have a p value because it's just an x squared, but my q is equal to negative 4. So that means my vertex is always pq, so it's at 0 and negative 4. Oh, better change color. Here is my vertex. Because a is negative, my graph has to go down, so then it'd be the same thing. It'd be over 1, and then over 2, 2 and 4, and then you would draw your graph like so. Okay, number 5, y is equal to negative 0.5 x squared plus 4x plus 8. So if you put these in your calculator, and that's what I would suggest doing right now. I don't have the emulator on this computer, so I can't put it on there. So I'm just going to draw it for you. So my vertex is at 4, 0. Is that 4? Okay. And then this point here is at 8, 0, and this was 4, 6, 8, negative 8, 8. So that's y is equal to 0.5 x squared plus 4x plus 8. So my b is a negative 2x squared plus 8x minus 4. So if you remember from our a values before, if a is, whoops, is greater than 1, you have a narrow graph. And if a is less than 1, you have a wider graph. So this graph that I drew, the purple one, a is a half, which is less than 1, so that's wider than normal. This next one is a 2, or the absolute value of it is a 2. So then that means my graph is going to be skinnier or narrower than normal. So for this graph then, my vertex is up at 1, 2, 2, 3. And again, if you do this on your calculators, that's where you're going to get these points, and you can just trace and find them. So it's a skinnier graph because my absolute value of a is greater than 2, and it's going, or greater than 1, and it's going down because it's a negative. Okay, y is equal to x squared plus 6x plus 6. So the vertex here is at negative 3 and 3. I'm going to go over 2 and up 4, 1, 2. So because my a is a 1, I do my normal up 1 over 1, up 2 over 2, up 3 over, sorry, I said those wrong. Over 1, up 1, over 2, up 4, over 3, up 9. So this is y is equal to x squared plus 6x plus 6. For b, got a negative value, so I know my graph's going to go down. I know it's going to be a normal width because absolute value of a is equal to 1. So the vertex is at 1, 2, 3, and 4. So there's your vertex, and then it's just over 1 down, 1 over 1 down, 1 over 2 down 4, and then 3 and 9, 4. So then your graph looks something like that. Okay, so that's for quadratics. And if you need more review on the quadratics, I can give you some more work to do on that one, just as a refresher for how to draw those. But for the most part, what we're going to be looking at, you should be able to do most of this on your calculators. So example number 7, y is equal to x cubed. So it's a cubic function with my vertex, so this is like x cubed plus 0. So my vertex is going to be here, but with a cubic function, you'll have points there, and it's going to do a kind of a curve. Oh, I do have a point up here that I can... and then going down, like so. So that's y is equal to x cubed. For y is equal to x cubed plus 6x squared plus 12x plus 9, what you find there is a shift. So it's over 2, up 1, and then my points from there. Because it's over 2, up 1. So over 2, up 1 got me that one, and this one here was over 2 and up 1 from there. So my graph behaves like so. Question number 8, for example 8, it's negative. So you notice that for both of these I have negative, so that means my graph is going to change behaviors. So instead of starting negative and going positive like it did in example 7, it's going to flip and start positive and negative. So y is equal to negative x cubed. We'll have here, here, and here, and then up. So the graph is going to go like so. Let's pretend it actually went through those points. So that's y is equal to negative x cubed. For this one, again, you're going to have that same negative slope to it, but everything is just going to be moved over. So this one is going to go over 2. And again, you can do this on your graphing calculator to get those points that I've graphed in there. I seem to have lost the graph for number 9. Oh, there we go. y is equal to x cubed plus 3x squared. So this one doesn't have, there isn't a, this is like plus 0x plus 0. So because it doesn't have those other values in there, it's going to cause your graph to have a little bit of a different shape. So the first point that you're going to see is going to be here at 3, 0. And the graph is going to go up 4 and over 1. And then it's going to go, over 1 down 2 through the origin and then back up. So 4, 1. So it's going to be kind of this type of behavior. Y is equal to that negative x cubed plus 3x squared plus 4. So this 4 and this 0 here, that tells you where your y intercept is. So this one occurred at 0 where it crossed that y-axis. This one will occur at 4. Negative means that it's going to flip behavior. So this one started negative, went down to the 0, to the x-axis, and then turned positive. So this one's going to do the opposite. It's going to start positive, come to the x-axis, and then go up positive, and then go back down to the end up in the negative. So I know my y-intercept is going to be at 1, 2, 3, 4. Then my other points are just going to be here, and these would be based on inputting values and finding your points. So the graph is going to do this. And then number 11, y is equal to x cubed plus 2x squared minus 5x minus 6. So you'll see with this one, the difference between this one and number 9 is just going to be a little bit the way the graph is stretched. Okay, in this question here, we had our kind of our graph changed directions in there. You'll see in question number 11, it's going to change directions the same number of times, but it's just going to be stretched out a little bit. So we have a point here at 3, 0. We go up 3 and over 1, down to 0, and then down here it goes on the y, so down to negative 6. It's going to go down 2 more and over 1, and then back up till it crosses at 2. So our graph is going to go more like, here's my, there. And question 12, I forgot to do that example, but basically it's going to be the flip of this one. So it's going to be going more in that direction because of the negative value on in the front there. Okay, so some things to keep in mind about polynomial functions. Polynomial functions are named according to their degree. And the degree is the highest exponent. Normally written so that the powers are descending. And your y can be replaced by fx or function of x. So your degree then is determined by the highest exponent within the polynomial function. So types of polynomial functions. We have a constant function. So that's when you have f, say like fx is equal to 3, or f of x is equal to 3 times x to the power of 0 if you wanted to think of it that way. So our degree for this is 0. So this would just be a straight line. It'd be graphing y is equal to 3, so it'd be a horizontal line going through 3. A linear function, so that's like f of x is equal to 2x plus 1. So that's like having it if you wrote it with a power, 2x to the power of 1 plus 1, so degree is 1. A quadratic, so that's like f of x is equal to 2x squared minus 4x plus 5. So quadratic means that your highest power is 2, so your degree is 2. And then we deal with cubics. And we do go higher than that, but those are the 3 main ones. Well, I guess 4, constant function too. So example of this is fx is equal to 5 x cubed minus 4x squared plus 2x minus 1. So degree for this is 3. Your domain has never changed. It's all possible x values. For the polynomial. Whoops, values. Another way of thinking of it is all possible input values. So an example could be domain set of values for x such that x is an element of real numbers. Your range is all possible y values for the polynomial. Or all your possible output values. So your example here, your range is a set of values for y such that y is, say, greater than or equal to 1. Y is an element of real numbers. Okay, so that's it just for kind of the refresher on polynomial functions.